Hey everyone, so this is the final section in chapter 2 that we're going to work on. This is 2.6, proving geometric relationships. So in the last section, we focused on algebraic proofs, okay, where we just really solved equations, talked about midpoints a lot, and segment addition postulate. But now we're going to be proving further geometric proofs, okay? So we want to really use that list that is in the week 9 folder that lists all of the reasons for proofs. In 2.5 we introed proofs. So here we're just going to practice some more and we're really going to get the hang of it. I know we can. You guys got this. So let's get started on the very first one. Okay, what we want to do is we want to write a 2-column proof. This mixes some geometry and algebra in this one proof, okay? Notice the statement's already completed. We just need to work on the reasons, okay? First, let's understand what information was given. So, given information we know is always the first thing, okay? It says T is the midpoint of SU. So here's T. They're telling us it's the midpoint of the segment SU. Okay, that's our given, so we can always start that off with our reason. Okay, the first reason is always given. The next statement says segment ST is congruent to segment TU. Okay, think about why can I say that this length of segment ST is congruent to segment TU. Hopefully you're thinking about the definition of a midpoint. They just told me T was a midpoint. Why is that helpful? Because now we know that ST is congruent to SU. Notice our third statement. Now we can say more than the segments. So now that the segments are congruent, but the lengths of the segments, by definition of congruent segments, they are now equal. ST, we can say, is equal to TU, okay? By definition of congruent segments, we know congruent segments mean they have equal lengths, okay? So now what we can say is we can say, well, what is ST? Notice how ST has 7x and TU has 3x plus 20. So notice in for ST we wrote 7x, in for TU we wrote 3x plus 20. And my reasoning for that is the substitution property. Okay, by substituting in those expressions for the segment lengths, we can now create this equation. Okay, check out what happened next. Notice now, instead of saying 7x equals 3x plus 20, it says 4x. So what did they do to both sides? Hopefully you're looking at that 3x, right? They subtracted the 3x from both sides. So that's the subtraction property. Notice now, how do I get that x by itself? Divide by 4 on both sides. That's the division property. And notice now we have proved what we wanted to prove. X equals 5. We always end up with what we were trying to prove. Okay? These will become more easy to identify as we practice. Don't you worry. Let's look at another one. Okay? The next one we want to talk about is now a geometric proof. So they're telling me what's given is that AC is equal to BD. So we need to prove that AB is equal to CD. And now let's start. The statements are completed. We just need to identify what the work is that they're doing. We know we always start with the given. Now think about what this says. This says that AC equals equals AB plus BC. What is that called when we add parts together to give me the whole? Notice they did it again. BD, that whole thing, equals what happens when I add BC and CD together. What is that called? Hopefully you're thinking about the segment addition postulate. We got to know that one by now, guys. Segment addition postulate, when we add the segments together to give me the whole thing. The third statement now, notice we just said AB plus BC equals AC. And now we said that BC plus CD equals BD. So notice what we did was we substituted those expressions into statement 1. Okay, we substituted what we wrote for the statement 2 in for statement 1. Substitution property. Lastly, notice there is a BC on both sides. So now there isn't a BC on both sides. So what did we do? We subtracted BC from both sides. That's the subtraction property. Okay, it's all about looking at the steps prior, putting the steps together, making connections between the statements, and then getting used to what our possible reasons are. There's that whole Google Doc, guys, that you want to have printed out so you can access it when you complete proofs. The next topic, really a vocab word I want to talk about is a theorem. Okay, so a theorem is a conjecture or a statement that you prove to be true. Okay, versus, remember we talked about the definition of a postulate. That's something we accept to be true but don't need to prove it. Okay, we proven to be true by writing a proof. So we prove theorems to be true with a proof. We can't use the theorem we're trying to prove in a proof, just a side note, as a reason. So we write a full proof to prove a theorem without using that theorem itself. So now I'm going to give you a few theorems that we want to really get used to and understand. The first one is the right angles congruence theorem. And this one's kind of silly. It just says all right angles are congruent, which we know, guys, because all right angles are 90 degrees, right? So obviously 90 degrees is congruent to 90 degrees. So that's the right angles congruence theorem. The next one is the congruent supplements. Congruent supplements, bear with me on this one. It says if angle 1 is congruent to angle 3 and angle 2 is also supplementary. So it's all supplementary. So angle 1 is supplementary to angle 3 and angle 1 is also supplementary to angle 2, then we can say, and look at it, angle 3 and angle 2 are congruent. So if two angles are supplements of the same angle, just like 2 and 3 were both supplementary to angle 1, then we can say that 2 and 3 are congruent. Same thing for complementary. So here's this example. If 1 and 2 are complementary, and 3 and 1 are complementary, then we can say angle 2 is congruent to angle 3. If they have this, they'll have the same measure because they're both complements of angle 1. The next theorem is my favorite theorem, and we're going to use it very frequently, is the vertical angles theorem. We know that vertical angles are congruent. So if we have lines that are intersecting each other, it forms congruent angles, and this tells us that vertical angle 1 and 3 are congruent, and 2 and 4 are congruent. They have equal measure when they're vertical angles. And lastly, we have the linear pair postulate. The linear pair postulate tells us that angles that form a linear pair are supplementary. Okay, so angle, doesn't matter what angle 1 is, doesn't matter what angle 2 is, but I know they're supplementary and they'll add up to 180. Okay, so if they form a linear pair, they are supplementary. We're going to use these theorems and postulates in the proofs that we're going to work on next. So let's see, this next one says angle 1 and 3 are vertical angles, and we can see that's true. Angle 1 and 3 are vertical angles. Prove that they are congruent. Okay, so we're going to prove that theorem. Remember, we can't use a theorem in a proof to prove it. We have to use other definitions. So let's look at what we have. Remember, we always start with our given. Our given told us that angle 1 and angle 3 are vertical angles. So that's our first statement. Now let's complete our reasons. What can I say here? 1 and 2 are supplementary, and 2 and 3 are supplementary. We can say they're supplementary because check out, aren't they a linear pair? Right? They're on angle 1 and angle 2 is a linear pair, and 2 and 3 are a linear pair. So by the linear pair postulate, we can say that we have supplementary angles. Now, how do I know that they add up to 180? Well, we know, well, what does supplementary mean? What supplementary tells me that they add up to 180. So by definition of supplementary angles, because what I just said, we can say by definition of supplementary angles, they add up to 180. My next statement, it says 180 equals measure of angle 1 plus measure of angle 2. Also 180 equals measure of angle 2 and measure of angle 3. So doesn't that mean we can substitute those 180s and then set these two expressions equal to each other? It does, and that's by substitution. Okay, by the substitution property, we can set measure of angle 1 plus measure of angle 2 equal to 2 and 3. Notice, guys, there's 2 on both sides. So we can subtract measure of angle 2 from both sides by the subtraction property. And lastly, when we go from measurements of angles being equal to each other, by definition of congruent angles, we can say angle 1 is congruent to angle 3, and that's what we were trying to prove all along, by definition of congruent angles. Okay, one last one I'm going to practice with you guys. It's not another proof, it's practicing vertical angles are equal. So another great thing about theorems is that we can use theorems to solve problems. We can use them to solve problems, and we're going to practice that here. We want to solve for x. Notice there's our x. The first thing we want to do is notice that we have vertical angles, right? Notice this angle and this angle are vertical angles. What do we know about vertical angles? We know vertical angles are equal. So our equation we can say is 3x equals 2x plus 40. And we can go ahead and solve for x. So what should I do to both sides? How about we combine our like terms? So I'm going to subtract 2x on both sides. So I'm going to get 3x minus 2x gives me x, 1x equals 40. And there we go, we solved for x. So that's the great thing about those theorems, is that we can use it to solve diagrams, to solve for variables, and that's what we're going to do a lot in 2.6 and moving forward this year. Okay, great work, guys. Take a photo of your notes, make sure you got everything written down, and you'll be submitting your notes to Schoology. Great work.